You're watching a Channel 98 NBISD TV production.
Welcome to another episode of Deja Vu, it's Algebra 2. I'm not your usual host, Kevin Corpy. I'm Tate Corpy. Remember me from episode 6? And my dad is on his spring vacation. Not to worry, I know what I'm doing. And besides, we've got satellite coverage of my dad as he travels the globe. So we'll be checking in on him with him often. Anyway, today we're going to be learning about different ways to represent functions and how to read graphs. So stick around and join me, Tate Corpy, for another great episode of Deja Vu, it's Algebra 2. What? Oh, I just got word that we've got my dad live via satellite. He's apparently in Las Vegas. That explains why he left me behind. Let's go to him now. Dad?
Hey Tate, thanks for the great introduction. I hope everything back there in New Braunfels is going well. You know, I really wish I could be with you back in New Braunfels. Actually, kind of wish you were here with me. Actually, no, it's fun to be here. This is no place for kids. But tell your mother I said hi and take care of the pets while I'm gone. I'll be back soon, okay? All right, yeah, well, actually I am here in Las Vegas, even though it looks like I am in Egypt, and that's because Vegas is such a wonderful place for great architecture. There's also a lot of math in Vegas, and the reason I'm standing in front of the Luxor Hotel is because a good hotel manager has to rent these rooms out to make money. Now, the number of rooms that he can rent out on any given night depends on the price of the room. And the price of the room is going to be very important in the amount of revenue that a good hotel manager will make on a given night. Okay, so the price of the room, number rented generates revenue. So as a good hotel manager, you're going to want to maximize the revenue. That's the amount of money that's coming in. Well, how do you do that? How do you know which price to set the rooms at so that you're going to maximize revenue? If you raise the price of the rooms too high, it's going to be too high and people aren't going to want to pay that money to stay there. But if you raise it too low, you're going to fill up the rooms and you're going to be wondering yourself, could I get a little bit more per room? Well, so that's kind of a mathematical model. Now, a good manager would probably look at the different price rates and take in the values of all the revenue he generated on a given night. That would be the data. Once you have empirical sets of data, what you could do is you could plot those data points on a coordinate grid. And that allows you to visualize or see the pattern. And once you have a pattern, you can actually do what's called a regression equation and write an analytical mathematical model that describes the situation. And once you have the equation of the model, then you can use that to extrapolate or interpolate or to answer questions where otherwise you'd just be taking a shot in the dark. The data table that's showing right here shows the cost per room per night and how much revenue that hotel brings in on a given night. And I've got that right here. So $200, he brings in $21,000 a night. That's a lot of money. $210, $22,400 a night. $220, $23,400. And $230 a night for one of these rooms, he generates $24,000. So notice that as the price of the room goes up, the amount of revenue brought in per night goes up. But will that pattern continue indefinitely? Think about it. If you charged $1 million a room, would he still be making money, or people say, hey, I can go down the street for less than that? The answer is, well, there's going to be a nice price level where he's going to maximize profit. He's going to rent out as many rooms as he possibly can, and there's going to be a balance between the price of the room and the number of rooms rented, and that's going to maximize his revenue. Now, let's go ahead and take that data and plot it in a scatter plot. Now, the scatter plot that you see here is graphed in a nice friendly viewing window. And if you look at the points, you can see that they're increasing from left to right. As the price of the room goes up, the points are increasing, or the revenue per night is increasing. But notice that it's not a linear curve. It appears to be increasing at a decreasing rate. It's kind of curved downward, all right? So once we have that pattern, you might ask yourself, if it's not linear, what else could it be? Well, in this case, it's a quadratic model. So you could actually go to your calculator or some program and write an equation for a quadratic. You can even do it by hand by using your ax squared plus bx plus c and plugging in 3 points. Okay? But if you do that, you're going to get a nice equation and a nice curve that passes through it, like this one here. Now once you have that, you have your model. You can see that it's a parabola opening down. And we're trying to maximize the revenue, which is at the very top, or the vertex. And we remember how to find the vertex by hand. It's just negative b over 2a. That's the x-coordinate. Or you can do it on your graphing calculator by finding the maximum. And once you do that, you get the next graph, and you can see that the vertex is at the point 240, 24,200. And what that means is the hotel manager, to maximize his revenues, should charge $240 per night per room, and that will maximize his revenue, allowing him to bring in $24,200 per night. And that doesn't include slot machines. That's just the rooms themselves. Okay? So mathematics, you get data, empirical data, you observe data, you collect it, you plot it on a scatter plot, look for a pattern, write an equation that fits the data, and then you can use the equation to answer questions. Okay? That's the wonderful power of mathematics. That's it from Vegas. Back to you, Tate and New Braunfels, in the studio.
Being able to read and interpret data in graphs is an important skill. Let's take a look at a single graph in several different ways. Huh? What? Oh, okay. I've just got word that my dad has left Vegas and is now in China. It's amazing how fast one can travel with a green screen. Dad, are you there?
Hey Tate, yeah, thanks for the great intro again. Here I am in China, standing on the Great Wall, one of the few man-made objects visible from space. Hey up there. Yeah, I doubt they see me. Anyway, I'm here in China on location just to bring to you mathematics in action. Okay? We're going to take a look at a graph, and we're going to assume that the graph is a cross-section of the Great Wall of China. And we're going to be measuring on the x-axis the horizontal distance along the ground, and on the y-axis we're going to be measuring the vertical distance the wall is above ground. Okay? Let's take a look at that graph. All right, now notice on this graph we have several points on the x-axis, A, B, C, D, E, F, G, H. Okay? Well, we're going to be using those points to reference different values of x, which are going to be horizontal distances from where I am. Okay? And the height of this is going to be the height of the wall. And you can see behind me there's a lot of vertical terrain here in China, especially where I'm standing. So, if we're looking at that graph, I want to ask you a question at home. Where is the highest point on the graph? At what value of x? Can you see it? Pretty easy to spot the highest point because the graph itself represents a physical model of what we're looking at. So the highest point on the graph is going to be the highest point of the wall, which occurs at point B. Okay? And that's not necessarily where I'm standing. I think that's somewhere, I think it's right over there somewhere, and I'll be going there soon. Okay? Here's another question. Where, according to the graph, is the wall the steepest? That is, if you took a tumble going down the steps of the Great Wall of China, it's going to be where you'd be falling down at the fastest rate. Okay? Not a pretty sight. Okay? Well, what are your choices? Is it steepest at B when you're at the very top? No, that's actually pretty flat at the very top. It's going to be pretty steep at C. Down at E, it's not very steep. That's kind of a low point. G is another high point. F might be steep. Okay? But notice that between C and F, C is a little bit steeper. Okay? We're not necessarily looking in positive or negative slope. We just want to know where is it the steepest. So C is the steepest part of the graph. Okay? Pretty clearly evident from the picture. Now, here's a good question. If a river was to flow through the Great Wall, through this little valley right here, where on the graph do you think the river would actually flow? Would it flow at B? River flowing uphill? Not very likely. Okay? Where do rivers flow? Well, rivers flow because of gravity. So they're always going to find the lowest point, the nadir, if you will, and that's at point E. Okay? So E would be where a river would flow across the Great Wall of China. Perhaps underneath it, right? Now here's another question we can try to answer from the graph. Where along this wall, according to the graph, do you get the best photo opportunity? Well, there's no correct answer to that. We can't really tell from the graph. That depends on what you want your photo to capture. You could take a photo from point B and get a nice picture of the magnitude of the wall from up high. You could take a nice picture from point E looking up at the wall and you get an idea of how tall it is. You might enjoy a picture from point C. So that's a relative answer. The others are more definitive, okay? But that's reading that graph in one specific way. Here on the Great Wall of China, the x-axis is the horizontal distance, the y-axis is the vertical distance. They're both distances. One graph, interpreting it one way, and we're going to take a look at that graph a little bit different way. But I can't do it from here. Lucky for me, I get to travel somewhere else. So I'm going to send it back to you in the studio, Tate, and I'm going to take a stroll down the Great Wall.
Thanks, Dad. Let's take a quick commercial break and give Dad time to travel to France. While you're gone, think of this. Why did Sarah bring lipstick and eyeshadow to school? The answer after this.
I remember how much you said you liked wine.
Oh.
You don't have to be perfect to be a perfect parent. There are thousands of teens in foster care who would love to put up with you.
Yesterday, my friends told me to smoke some weed, and I did. Then today, they said I should try to outrun Tick-Tick, the little lumberyard dog. And I don't think I can. I'm an idiot. I'm doing stupid stuff, and that ain't me.
Live above the influence. Above them, above weed.
Welcome back to Deja Vu, it's Algebra 2. I'm Tate Corpy, hosting a show today because my dad's on vacation. We're talking about functions and graphs and why Sarah brought her a lipstick and eyeshadow to school. You want to know why? Because she had a makeup exam! Let's go to France.
Oh, thank you, Tate, back there in New Braunfels. Here I am in Le France, and it's a great place to be. I'm standing in front of a famous French icon, the Arc de Triomphe, and it's right here, okay? I'm not actually taller than it. I'm in the foreground, okay? It's way down the street. I'm going to go there in just a second. Now, what we're going to do here in France is take a look at the exact same graph that we looked at the Great Wall of China, okay? Same graph, but we're going to read it a little bit differently. Now we're going to call the x-axis time, not a physical measurement. It's going to be a time that it's going to measure the time that a bicycler, okay, a Tour de Francer, if you will, is going to spend on a bicycle traveling up and down this very straight road that runs north and south in front of me. Perfectly flat, perfectly straight, north and south, okay? The y-axis then is going to measure the cyclist's distance up north and back down south on this road from the Arc de Triomphe, okay? So the x-axis is time now, and the y-axis is distance north and south along a perfectly flat road from this monument, okay? Now, although the curve kind of goes up and goes down, the bicyclist does not. So in that sense, this graph is not a literal picture like a cross-section of the Great Wall, okay? We're going to have to read a little bit differently. So here's some questions for you. If the cyclist starts at the arc at time A on the graph, and he finishes back here at time H, how many times does he bike through underneath the arc, which is right here? How many times does he actually go underneath it? Well, let's see. He's going to be traveling away from the arc, let's say north, and how do we know when he's back at the arc? Well, if he started at A, that was on the x-axis. Okay, and at the x-axis, the y value is 0, which means his distance from the arc is 0. He's there. So where's the y value 0 again? At point D. He's back at y equals 0, which is 0 distance from the arc. He's back at the arc. Notice he's on the other side now. At F, he's back at the arc because his y value is 0. And at H, he's back at the arc. So how many times did he pass through it? He passed through it once at D and once at F. Okay? So he went through the arc 2 times. Now, how many times does he actually turn around? Where does this guy actually turn around? Well, he turns around when his distance from the arc starts coming back towards the arc. So notice at point B, he's going from further away from the arc north to further south back towards the arc. So he turns around at B. He also turns around at E as he starts going back towards the x-axis again. And at G, a third time, his distance starts going back towards the x-axis. So those are the turning points, the relative maximums and the relative minimums of the graph, those are the turning points of the bike rider as well. So he turned around 3 times and went through the arc twice. At what point is he riding the fastest? Ooh, well, how are we going to figure out how fast he's riding if all we know is his distance? Well, that's going to be where the graph is returning to the x-axis at the fastest rate. That's going to be the slope or the steepness of the graph. So where did we say the graph was the steepest? In China? It was at point C, which represented the steepness of the terrain. In this case, the steepness of the graph represents the point at which the bicyclist is traveling at the fastest rate. In this case, he's traveling at that fast rate back towards the arc. Okay, here's another question. According to the graph, does he spend more time north, way over there on that side of the arc, or south in the area where I'm at? Okay, well, how are we going to figure that out? We're looking for horizontal measurements of time. Notice from A to D, which is pretty wide, he spends north of the arc. From D to F, he's south of the arc, and from F to H, he's north of the arc. So he spends more time north of the arc, from A to D and from F to H. That horizontal distance is greater span than it is from C to F. More time on the north side. Did come to the south side just a little bit over here to tell me hi, and I waved to him. All right, question 4, last one from France, and then we got to move on. At what point did the bicyclist realize that it was dinner time? According to the graph? Well, again, that's kind of a relative question. We don't know what the bike rider's thinking. He might be hungry the whole time. But if you're going to answer the question, maybe you could say at point G. Remember, at point G is when he turned around and he started coming back towards the arc. Maybe that's when he started getting hungry. He realized it was dinner time, finished back at the arc at point H, got off his bike and went for some le French fries or something like that. Okay? They've got good potatoes here in France. So anyway, one graph read a little bit differently means something entirely different. Okay? Reading graphs is very important, and in doing so, it's important to very clearly and conscientiously ask yourself, what are we measuring on the x-axis and what are we measuring on the y-axis? That's all I have from France here, Tate. Back to you in the studios.
Thanks, Dad. Now it's time for my favorite part of the show, the ending. No, just kidding.
Deja Review.
Let's go to Dad on location in Rome.
Hey, thanks, Tate. You know, back there in France, talking about food and all that stuff, it kind of made me hungry. So I got to roaming around and ended up here in Rome. Hey, what do you know? Well, you know what they say, when in Rome, go to the Colosseum, as the Romans do. So anyway, here I am. Now, I'm at the Colosseum, the ancient Colosseum, for a very specific reason. We're going to be looking at that same old graph again. Yeah, you guessed it. But we're going to be looking at something different. Now, how is it going to pertain to the Roman Colosseum? We're going to be talking about a Roman gladiator. And we're going to be talking about time again on the x-axis. But this time, the variations in the y-axis, or the y values themselves, are going to represent the velocities, not distances and not position in relation to the arc, but velocities of the gladiator at any given time. Now, velocity is kind of like speed, but speed is non-directional. You can be going this way, that way, left or right, up or down. Velocity is directional. And we usually talk about a positive direction and a negative direction. So a positive velocity is speed in a positive direction. Negative velocity is speed in the opposite direction. Doesn't mean he's running backwards, although he could, but he's running the opposite way from the positive direction, okay? So in this case, the positive y values on the graph are going to mean that the gladiator is moving forward. He's charging with the spear or something, okay? The negative y values are negative velocities, and that means that the gladiator is going to be running the opposite way or retreating, okay? And the x-axis is time, so he's going to be moving forward and backwards. So now that we have that all established, here's my question to you. When is he moving the fastest? That's when is his speed the greatest. Now remember, we're measuring velocity on the y-axis. Velocity is directional. So what we're looking for on the graph is where are the y values the furthest away from the x-axis in any direction. Doesn't matter if it's as high above or lower below. Okay, we're looking for the point that's furthest away from the x-axis. Well, the two candidates are really, or the three candidates are B, E, and G. But notice that B is taller than G on the graph, so it can't be G. What about B and E? Well, E is quite a bit away from the x-axis, but B is further away from the x-axis. So the answer is the gladiator is moving at the fastest velocity or the fastest speed in the positive direction at B. Okay? Got it? Now, here's another question. How many times does the gladiator turn around? we can't be looking at the relative extrema this time like we did for the rider in France. In this case, the gladiator is going to turn around when he goes from a positive velocity to a negative velocity, right? He's running forward at positive velocity. He has to turn to retreat, right? So when you turn to retreat, what's your velocity? Assuming you don't want to sprain an ankle or blow out a knee, it's got to be 0. So graphically, we're looking for a place where the graph crosses the x-axis from positive to negative or negative to positive. That's when the gladiator's turning around. That's going to happen at D. He goes from charging to retreating at D. And at F, he goes from retreating to charging again. What happened there? So the gladiator turned around 2 times. Those are the x-intercepts, okay, where the graph actually crosses the x-axis. Another question. At what point on the graph is the gladiator the furthest away from his starting point? Ooh, okay. It could be that he moved forward and came back and passed where he was in the other direction. So what we're looking for is, let's see, he was running forward from A to D. He was running in the opposite direction from D to F. So he's heading back from where he came. And then he turns around at F and runs in the same direction that he originally did towards H. So think about it. If you're moving forward for a long time, you turn around and come back for a little bit, and then you turn around and come forward again, but not as much, where were you the furthest from your starting point? Well, that's going to be at D. Now, if you want to think about this in terms of another way of looking at the graph, what we're looking at the areas under the curve. And we want to know where is the area under the curve the most positive. So clearly, from A to D, we're picking up a big chunk of positive area. We're canceling some of it back out from D to F, because under the x-axis is negative velocity, so we're heading backwards. We're losing some of the ground we gained. And then from F to H, we're going back. And notice from D to F and F to H, they're almost about the same size. So those almost cancel. So we're running up, we're charging, we turn around, we run back maybe 3 steps, turn around, run forward again 3 steps. Okay, so it's kind of a wash. So he's furthest away at point D. Now here's one of those great questions. Where does the lion come in, right? What would a gladiator, Roman gladiator, be without a lion to fight, right? Well, again, that's one of those questions. You can make up something fanciful from the graph, use your imagination. Maybe the lion came in at D when he was charging, saw the lion, and turned around and ran the other way. But maybe you say, hey, Roman gladiators don't retreat from lions, so maybe he was bummed out, didn't think a lion was coming, started walking back, and the lion came out at F. And that's when he turned around and started charging at it again, right? You could say that. Or maybe the lion came in at H. What happens at H? His velocity 0 and the graph ends. So, I'll let you use your imagination on that one. Anyway, I'm going to roam around Rome a little bit longer. Thanks for coming out here with me, and I'm going to take in some more sights. All right, that concludes a fantastic spring break episode. Wouldn't you agree, Tate?
Yes, sir.
Yeah. By the way, Tate's with me now. He got to leave New Braunfels, and we're standing right now on the beautiful beaches of Dubai. It's a great place. Now, I hope you learned today that whether you're on spring break or it doesn't matter where you are in the world, math is where, Tate?
Everywhere.
Math is everywhere. Now, even though you're on spring break, you don't want to go 7 days without doing any math, because you know what they say, 7 days without math makes one...
Full week.
Makes 1 week. Full week. Yes, it does. Anyway, we're here to say goodbye from
Dubai.
Goodbye from Dubai. And until next time, I hope you'll join me. But until then, I'm Kevin Corpy,
I'm Tate Corpy.
reminding you to do your homework.